Hey, how's it going? Today we'll continue moving up the ABI's most wanted list by feeding your curiosity with more malware stuff. So, a couple of days ago, I woke up, got caffeinated, took my favorite type of therapy, and sat down to watch some of MrBeast vids. And after a while, I noticed that MrBeast thumbnails are really appealing to a lot of people. And this is when I thought of a way to use them to troll some of my friends, or to launch some phishing campaigns to hack reward targets. So in this video, I'm going to show you how you can fit malware or malicious code inside an image. But before we begin, I know there are many other ways to do this, but I believe this is one of the simplest ways you can use to hide malicious code inside an image. Now let's begin by choosing an image to hide our malicious code. I'll go with this MrBeast image. Next thing we need to do is to get our shellcode. I have the shellcode here that launches calc.exe when executed. We can have the shellcode do anything we want, such as dropping a malware or getting a reverse shell to a remote host. But we'll stick to this one for this video so that YouTube doesn't do anything harmful to us. The next thing we need to do is to encrypt this shellcode to hide its true purpose. Don't worry, we're not going to use any complex cryptography. We'll just go with a simple XOR encryption. So I put together a simple Python script that takes our shellcode and outputs it like that, and I'll tell you why in a sec. But first, essentially what's happening here is that we loop through the shellcode and XOR encrypt each byte using our key here, and then we print out the encrypted shellcode. Next step is to load the image into any hex editor. I'm using HXD here. Once the image is loaded, copy the encrypted shellcode and scroll down to the very bottom of the image and paste in the encrypted shellcode, and make sure to save the changes. Now, the reason we inserted the shellcode at the end of the file is because we don't want to corrupt the image signature. Have you ever asked yourself how does the file command figure out file types? Well, each file has its own signature. This signature is a bunch of magic bytes that indicate the file type. The file binary takes these magic bytes and looks up what they map to in its database of file signatures. That's why we can insert our shellcode at the beginning of the image file, because it will override signature and hence making this image file even more suspicious. For example, I have these two identical images here. The first one has the shellcode inserted at the beginning of the file, and the other one has the shellcode inserted at the end of the file. After saving the changes, we can see the first image is no longer identifiable and doesn't work either. On the other hand, the second image with the shellcode inserted at the end of the file is still identifiable and works just fine. The next thing we need to do now is to hide or embed this malicious image in a portable executable file, which brings us to executable resources. The portable executable file consists of headers and sections that tell a lot about the binary. Relax, don't panic. We won't go through any sophisticated matter regarding the PE file format. What I just want you to know is that the headers store information about the binary, such as the architecture, the executable checksum, number of sections in the binary, and so on. The sections, on the other hand, serve one purpose. Each section stores a specific type of data. For example, the text section stores the code that will be executed at runtime. The data section stores the initialized global and static variables, and so on. The section that matters the most to us in this video is the RSRC section, or the resources section. This section stores all the resources related to the executable, such as icon image, bitmap images, dialog boxes, and so on. What we are going to do now to take advantage of this section is that we will take our malicious image and store it inside this section. And at runtime, we will extract this image from the resources section and retrieve our encrypted shellcode, and then we decrypt it and have it executed. But first, let's build the executable that will store our malicious image. Here we have two simple functions that make all the functionality we need. And as always, let's visualize what happens in memory when each line of code is executed. The first one API we have here is find resource. This API is used to find a specified resource in a resources tree. It takes in three parameters. The first one is the base address of the module that contains the resources tree, which in this case is the executable base address, or the memory address in which the executable is loaded. We can obtain this address by using the get module handle API, which returns this address for us. The second parameter is the name of the resource that we are looking for, which in this case will be MrBeast. The last parameter is the resource type. From the Microsoft documentation, we can see there are various resource types. But since we are using an application-defined resource or a JPEG image, which is considered raw data, we use the RTRC data type. If this API runs successfully, it will return a pointer to the information block of the specified resource. This information block contains the base address of the resource or the address to the first byte of the JPEG image. So the next API we need to use to obtain this address is the load resource API. This API takes in two parameters, the base address of the executable and the pointer to a resource's information block, which we obtained from the find resource API. If this API runs successfully, it will return an indirect pointer to the base address of the resource. So now, to obtain the direct pointer to the first byte of the resource, we use the lock resource API. It takes in the indirect pointer that we obtained from the load resource API, and it will return the final pointer which we will use to access that resource and manipulate in any way we want. If any of these three APIs confuses you, you can think of them like that. The find resource API locates the resource in the executable. The load resource API prepares the resource for use, and the lock resource API provides direct access to the resource data. Now, since we have access to our resource or the image that contains the shellcode, we need to extract this shellcode. And to do that, we first need to get the resource size in bytes. So next, we use size of resource API, and we give it the base address of the executable and the pointer to the information block, returned by the find resource API. If it runs successfully, it will return the resource size in bytes. Keep in mind that this size is the size of the image and the shellcode combined, and we only want to extract the shellcode, which means we need to know the size of the shellcode in bytes. That's why I hard-coded the shellcode size in a macro here. You can easily get the size of your shellcode in bytes using Python like this, but make sure the shellcode is divided to individual bytes like this, not like that. Now, in order to extract the shellcode from the image, we first need to move the pointer returned by the lock resource API to the first byte of the shellcode. For example, let's say the resource size is 60 bytes, 40 bytes for the image and 20 bytes for the shellcode. We know that the pointer returned by the lock resource API points to the first byte of the resource, and we only want to copy the last 20 bytes of the resource, which in this case is the shellcode. So all what we have to do here is to move this pointer to the first byte of the shellcode and read 20 bytes from here. And that's exactly what we're doing here. We first typecast the pointer returned by the lock resource API to long pointer to byte to be able to do pointer arithmetic operations. Then we subtract the shellcode size from the resource size and add the result to the pointer to move it all the way to the first byte of the shellcode. Keep in mind that when we subtract the shellcode size from the resource size, we end up with the image size, and we want to completely ignore that. The next thing we need to do now is to decrypt this shellcode. At the beginning, we used a simple Python script to XOR encrypt the shellcode using the key secret. So to reverse that, we first define a byte array to store the decrypted shellcode and set its size to the size of the shellcode. Then we loop through the encrypted shellcode and we XOR decrypt it using the key secret and store the output in the shellcode byte array. Everything from here on is old news. Similar to the previous videos, we allocate enough memory for the shellcode using the virtual alloc API. Then we copy the decrypted shellcode to the allocated memory using the RTL copy memory API. Then we create a thread to execute the shellcode using the create thread API. And finally, we halt the execution of the program until the thread returns using the wait for single object API. And then we close the handle to the created thread using close handle API. Now to compile this code, make sure the architecture is set to x64 and the build is set to release, not debug, and then build the solution. Now, after the executable is compiled, we need to embed the malicious image inside it. We only implemented the logic that will extract the shellcode from the image, and this executable doesn't contain this image yet. So now, we first make sure we have the image that has the shellcode inside it, and then we open Resource Hacker, a program that allows us to manipulate executable resources. Open the compiled executable, add image resource, select the malicious image, set the resource type to RC data, and make sure the resource name is the same as the one in the executable, which in my case here is MrBeast. If you notice here, I can only write uppercase letters, which is fine, nothing will go wrong. Once you click on add resource, the malicious image should be embedded in the executable. Now, moment of truth. Once we run this executable, we can see the shellcode is executed and calculate.exe pops up. Congrats everyone, we just moved up the FBI's most wanted list. Now you know what are executable resources and how you can use them to conceal malware presence and make your malware stealthier. And we barely scratched the surface on this one, by the way. We didn't implement any fancy encryption, we didn't use any advanced injection techniques. This was just a warm-up. I'll leave anything else to your imagination. As always, you'll find the code along with a compiled executable on my GitHub, link in the description below. I also wanted to tell you about... Hey, Seth, do you hear that?
The FBI is here, let's go!
Alright guys, I've gotta run now, but before I go, make sure to like, share, and subscribe, and if you like this content and want to see more of it, make sure to support us by becoming a member here, or you can check our Buy Me a Coffee link in the description below. Hopefully I'll see you in the next one if I didn't get caught.
Hurry up, man, let's go!
Coming! Through the back door. Come on. Hurry!